Howdy. I wanted to work number 43 because it's a really good problem for illustrating some advanced ideas in analysis. Take a look at number 43 here. After a completely inelastic collision between two objects of equal mass, each having initial speed v, the two move off together with speed v over 3. Now the question is, what was the angle between their initial directions? And you can see I've already underlined the angle here, because that is giving us a context clue that we are working in 2 dimensions. And so our before diagram looks something like this: object of mass m, object of mass m, speed of v, and they now come together and move off in some direction with a speed of v over 3. And there are 3 ideas that I want to get across here. The first idea is choose a good reference frame. And the second idea that I want to get across is that you, as the problem solver, have the option of choosing polar or rectangular, whichever is most convenient for you. And the third idea that I want to get across is the idea of trig IDs for elimination. So let's take a look at each one of these ideas. First thing that I observe about my problem, the way I've drawn it, is that it's not very conveniently set up, because each one of my velocity vectors is off at some strange angle. So what I'd like to do is to take my diagrams right here, and I'd like to move them. Okay, that worked. Okay, let's group all that. Much better. I'd like to rotate this whole thing so that at least one of my velocity vectors is purely horizontal, and that way I only have 2 angles to worry about. This velocity vector is going to be at some angle theta, and this velocity vector is going to be at some different angle. Let's call that angle phi. Sure, why not? So this is part of choosing a good reference frame, is rotating the problem so that it becomes at least a little bit simpler. Now the next question is, do I want to use polar or rectangular form here? And when I was first working this problem, I wasn't really sure. And so I actually tried both. And it turned out that polar was more convenient, but you won't necessarily know that ahead of time. One big clue is that they're asking us to find the angle here between the 2 velocity vectors. So that suggests that polar form might be better, but that's not a given. And there are times when rectangular is best, and there are times when polar is best, and sometimes you just have to experiment. Let me show you what that looks like. I try it in polar form. Well, let's try it in rectangular form first. If I try it in rectangular form, then what I've got is e comma 0 for my first vector, and then I have, let's call this v1x and v1y for my other vector, and then the final one would be v2x and v2y, something like that. And so then when I express conservation of momentum, p0 equals p final, then what I get is, for the first object, m times v comma 0, plus for the second object, m times v1x comma v1y, and then for the final, 2m times v2x comma v2y. And when I look at this guy, what I see is that I have lots and lots of variables. M is given to me in the problem, so that's not an issue. V is given to me in the problem, so that's not an issue. But all of these 4 right here are variables, and there's nothing about this that expresses the fact that the 2 initially have the same speed. I ought to be able to see that somewhere in the diagram. And there's nothing about this that expresses the fact that the final speed is v over 3. So I can write the rectangular form easily, but when I look at it, it doesn't really express or capture the problem very well. And that told me, hey, maybe I want to try instead polar form here. The polar form would look like this. I still have v comma 0 for the first one, plus. And now, for the next one, I would represent the velocity as v cosine theta, comma, v sine theta. And that now equals 2m times v cosine, excuse me, v over 3 cosine phi, v over 3 sine phi. And I look at that, and I still have two variables here, theta and phi, but one of those variables is the variable that I'm looking for, and also I managed to sneak in the fact that I was dealing with a speed of v before and a speed of v over 3 after. And so it seemed to me that polar form was a better approach for this problem. And lo and behold, when I pursued it, it sure was. Let's now unpack our equation that we've got right here and see what it's telling us. I'm going to write it out so it's a little cramped on the side there. Okay, there's our equation. Now, the first thing that I noticed about this equation is that m is a common factor of every single term, and so I'm going to cancel it so that our masses cancel out. Isn't that nice? And the second thing that I notice about this is that I have really two equations packed into this thing because I have an equation for my x's, and I also have an equation for my y's. And those are actually two separate equations. So let's get those carefully. The equation for the x's is going to be that v plus v cosine theta has to equal 2v over 3 cosine phi. And the equation for the y's is that 0 plus v sine theta has to equal 2v over 3 times sine phi, like this. And what I notice about these equations that's really nice is that v is a common factor of each term, so that the v's also cancel out. And what I'm left with is a relatively simple equation that 1 plus cosine theta is equal to 2/3 cosine phi. And sine theta is equal to 2/3 sine phi. And that's not so bad. In fact, I like it because I have two variables, theta and phi, and I have two equations. And that means theoretically I can solve it. So now this brings us to our third point, which is substitution or elimination. And in this case, I'm going to use a clever trick based upon a trigonometric identity in order to eliminate variables. And the clever trick is what we call the Pythagorean identity. If you've already had me for calculus, you know this identity pretty well. If you have not, then it probably makes a whole lot of sense. If I take any right triangle and have an angle theta and label the sides opposite and adjacent and hypotenuse. So opposite over here, adjacent here, and hypotenuse there. Then the sine of theta is equal to the opposite over the hypotenuse, and the cosine of theta is equal to the adjacent over the hypotenuse. Now, I want to observe something, and that is that in this right triangle, opposite squared plus adjacent squared is equal to hypotenuse squared at all times, because that's the Pythagorean theorem. If I divide through by h squared, then I get something remarkable, because O squared over h squared is the square of sine theta, and a squared over h squared is the square of cosine theta. So that we end up with what I call the Pythagorean identity, that no matter what angle the square of the sine of that angle plus the square of the cosine of that angle is equal to 1. This remarkable fact is actually really useful in this circumstance. What I'm going to do is to take these two equations right here and square them and add them. And when I square the top equation, I'm going to get 1 plus cosine theta squared equals 2/3 cosine p squared. And when I square the bottom equation, I'm going to get sine squared theta is equal to 2/3 sine p squared. Okay. Well, let's take those two equations and simplify them a little bit. Let me bring them down actually to a new page so that you can see them. I'll just write them again. So let's just simplify this algebraically. See if you can pause the video and beat me to it. Welcome back. When I square this side, I get 1 plus 2 cosine theta plus cosine squared theta equals, on this side, 4/9 cosine squared theta. And for the bottom equation, I get sine squared theta equals 4/9 sine squared theta. You may have noticed that I wrote the cosine squared, the sine squared directly underneath the cosine squared. And that's because when I now add this equation, the bottom equation to the top, something wonderful happens. Using the Pythagorean identity, these two add together to give me exactly 1. And when I use the Pythagorean identity again, these two add together to give me exactly 1. And lo and behold, my variable phi drops out of the equation, and I end up with a really nice, simple equation. 2 plus 2 cosine theta is equal to 4/9, or 2 cosine theta is equal to, do the subtraction, 2 is the same as 18/9, so negative 14/9, or cosine theta is equal to negative 7/9. And when you solve that equation on calculator, just a moment and let me do that. Seven divided by negative 9, and inverse cosine gives me 141 degrees. As the original angle between the two of them. So this was an interesting problem, and